Hello, everyone. Thank you, first of all, thank you for all of us for joining us today. I'm Vikas, I'm Senior SD at Amazon, and along with me is Paris, my colleague here. Together, we'll be walking you through the process of in-place shard splitting. I'll start with the problem statement, setting up the problem statement and context, talking about the current limitations in the existing system, and then we'll define clear requirements and goals required to build the solution. We'll go over the proposed solutions. As per the pros and cons of each of the solutions, we'll get to the implementation and design of the same. So these are the three major areas of the problem statement we'll be covering today: hot shards, prediction challenge, and current limitations in the existing solutions available for the users today to get out of the hot shard problem, and how that can lay foundation for building the in-place shard splitting. So one of the major problems which OpenSearch users face today is hot shard, where a shard grows beyond the node capacity, or they start hitting the 2.1 billion doc level limit, which start impacting performance, leads to slower searches, higher memory utilization, reduced indexing pressure, indexing performance. So to avoid this problem in future, users typically try to predict the number of shards, which is a homogeneous setting which is set during the index creation itself, which stays as a static setting throughout the life cycle of the whole index, which means that even if subset of shards become hot at one point, we don't have any dynamic sharding capability today as of now, which means that use cases such as which require custom routing keys and custom multi-tenant workloads or vector workloads. So in these cases where few of the shards become hot, which require further scaling, they don't have an option to move out of this cluster. They have very limited options. So they have this over-provisioning risk always, where too few shards or too many shards can always lead to significant performance impact. So since once users get into the hot shard problem, they have these two limited options available to them, both of which are not efficient. Reindexing, as we all know, is highly latent, highly compute intensive, and requires high IO resource usage. It is highly latent, as we all know, that it takes significant amount of time to complete. The other option available for the users is index split API. As the name suggests, that it works at index level, which means that all shards of the index are split, not just the shards which are hot, but we also end up splitting the shards even if they are small in nature, resulting into much smaller shards and leading to other performance issues. It also requires double the storage capacity, as the entire index is cloned to a new index, and cloning to a new index, splitting to a new index has another set of constraints. Moving from X number of shards to Y number of shards also has a certain constraint. Another major drawback of this API is write downtime, which means that users are supposed to put write block, which means they have to stop their write traffic before they can use this API. So these are the two limitations which exist today, and both of which we know are not efficient enough to get out of the hot shard problem. So based on the problems we have seen so far, these are the three major properties which we need to, as part of our target solution which we are building here. Reindexing, as we know, that it requires huge compute and I/O. So the solution which we are expecting should have a minimal resource overhead on the CPU usages and I/O constraints and other things. Index split API, as we all know, comes with a write downtime. So the solution which we expect, which we are building here, is expected to have zero downtime, which means users should be able to split without experiencing any downtime, any write downtime or search downtime. Third and last thing would be we should have granular shard level control. So we saw in the index split API that it works at index level, ends up splitting all the indexes. So we need a solution which can work at a shard level, target specific hot shards, and be able to split the selective shards instead of the whole index. There are a few additional properties which we require. Of course, we cannot afford any data loss, which means there should not be any data discrepancy between the parent shards and the child shards throughout the whole process of splitting. To ensure this, we will be leveraging some of the principles of peer recovery. This process is used in shard relocation, where a shard moves from node A to node B, and during the entire process, data consistency ensured by executing various lifecycle stages of the recovery. Another major factor which is needed to build this solution is routing consistency. Now that we know that we will be mutating existing set of shards, we'll need a different routing mechanism to route the docs which are earlier being routed to parent shard through the child shards now. Same goes for search traffic. So we need to either extend the existing routing mechanism, or we need to build a new routing mechanism to handle this routing. This leads to the operational benefits we talked about earlier. Users will no longer need to have the over-sharding or under-sharding provisions. They should be able to scale dynamically without thinking a lot, without worrying a lot about the number of shard setting, and they can simply start with X number of shard and scale further. This also leads to simplified cluster design, where they can take reactive actions based on their workloads at a later point without worrying too much today about how their indexes would grow in future. With this, I'll hand it over to Paras to talk about different approaches which are at hand, which we can go on exploring, which will explore and talk about different pros and cons. And based on after weighing out each of the options, we'll select the design and we'll go over the implementation details of the same.
Sure, thanks, Vikas. So let's go over the approaches that we have explored to tackle the problem at hand. I'll start with the first option, that is shard rollover. So the design strategy for shard rollover is to add a new shard corresponding to the shard that went hot. So for example, let's say we had two shards on an index, 0 and 1, and shard 0 grew hot. Now we want to add a new shard, that is shard ID 2, and mark the shard ID 0 as read-only for any new indexing operations. So as we see, the new writes will be routed to the new shard, that is shard ID 2, while updates can still be served from the older shard. And old shard, like shard ID 0, will still hold all the data, so hence searches will have to be routed to all the shards that are mapped to shard ID 0. Essentially, what we're saying is that the original shard IDs become logical IDs, and under each logical shard ID, we can have multiple shards which keep getting rolled over as and when they become hot. Let's see the design implications. So for shard rollover, we ran benchmarks and we could observe that with varying shard configurations, we saw search latency taking up to 200% of hit. Indexing was also impacted for use cases of custom routing and custom doc IDs and update-heavy traffic. And of course, the approach, since it only requires to add a new shard with no other operations required, so it's pretty fast to scale. Another thing that we thought about was the single writer semantic that we follow in OpenSearch against the shards. So in this case, since the same shard IDs, you will have multiple writers, that is for updates, as I gave the example earlier, right? So we'll have to serve the updates through the older shard, which essentially should have been read-only. And the new writes will have to be served from the newer shard. We have multiple writers now. This also creates confusion around concurrency handling. Today, OpenSearch only handles concurrency at the shard level, not across multiple shards. So this calls for a need to build a concurrency handling mechanism spanning multiple shards under the same logical ID. So with that, I'll move on to the proposed approach that we will discuss a bit more in detail. Cool. So I'll cover this approach in two different aspects. We have to, just taking a step back, so what do we do here? We actually are splitting the shard here. It's a physical split. We replace the older shard with multiple shards. And just to establish few terminologies, we are calling root shards as the initial shards of the index. So considering we create an index with two shards, 0 and 1, those are our root shards. Now, once we split a shard as it has grew hot, let's say we split shard ID 0, we create shard IDs 2 and 3. Those are child shards. So any number of shards, any shards created after a split are our child shards. And how do we now route our requests to the correct shard IDs, right? So there are two levels of operation routing here. So the first level operation routing is the root shard resolution, which remains as it is. We are not changing anything here. We are just using the hash and mod approach that works today for operation routing, and we resolve the root shard. What if the root shard is split? It's no longer active, right? So we will have corresponding child shards under the root shard. And that is where we use a logarithmic search algorithm. It's a binary search algorithm over the sorted shard ranges. And that is how we resolve the child shards. Now, how are the key spaces divided amongst the child shards? This is what we have illustrated below. So let us say we split shard ID 0 into 4 different shards. So at the first level of split, we assign the entire integer range to the 4 shards and divide them equally, as we see in the first diagram. But let's say we split the shard ID 2 into 2 more shards. So the key space range assigned to shard ID 2 gets evenly distributed amongst the newly created child shards, and so on. Like, so we support nested splits here. There's a limitation, though, that we can only support so many splits, but it's a very high number, and yeah, so it scales pretty well. The second aspect of it is to actually create the child shards, and we call it child shards recovery. So this is based on the existing peer recovery mechanism that we used, that is currently used to relocate shards across nodes, bringing up new replicas or moving the primary, etc. It's proven to be durable and reliable. Moreover, the physical split involves child shard recovery on the local node. So if we are splitting a shard ID 0, wherever the primary is hosted, we create the child shards as replicas on the same node. So it's essentially a local peer-based recovery mechanism. Here, the parent shard, which is undergoing the split, will be the source shard, and the new shards, the child shards that are coming up, are the replicas, like following the analogy of peer recovery here. So moving on. So these are the following phases of child shard recoveries. This is a bit like going to depth of the recovery flow. So again, the analogy is being drawn from the existing peer recovery flow. The phase 1 recovery for us involves acquiring the translog retention lock on the parent shard, the shard that is being split. So from here onwards, we will not be trimming the translog because we would later need it to be replayed on the child shards. The second step here is acquiring the last commit. Now, we are acquiring only the last commit on the parent, not a safe commit, because firstly, like, I'll just take a step back and explain what the last commit, safe commit would be. So safe commit is guaranteed to be having documents which are committed on all the replicas of the primary. But the last commit may or may not have documents which are committed on all the replicas. We don't need a safe commit here because we are anyways using this commit to bring up local replicas on the node. And essentially later we will be waiting for those shards to come in sync with the primary, thus ensuring durability. So the third step would be to hardling the segment files. Now, this is very much efficient. So we are not copying over all the data from the parent shard directory to the child shard. Since it's a local node setup, it enables us to just hard link the files from the parent directory into the child shard directory, and it's pretty fast. We are not using any extra storage as well here. And finally, we are using an existing construct which is used by the index split API, that is shard splitting query. What it essentially does is it fires update by query requests on the child shards and marks the documents that do not belong to the shard as per the operation routing algorithm that we discussed earlier as deleted. So yeah, we bring up the copies of the parent as child shards, and we mark, let's say if you're doing 1 to 2 split, right? So we will just mark 50% of documents deleted. Yeah. So this is the phase 1 recovery. We move on to phase 2. We have initialized the child shard directories. We have carried out a split. Now we initialize the engine for the child shards, and we add these shards into the replication group. Now, when we said that it is completely online, we have not stopped any indexing traffic on the primary. And now, since the child shards are ready, the engine is up, we just add them to the replication group, and the child shards receive every indexing request that the primary is serving. It is replicated to child shards, and all the documents are in the child shards as well, the new documents. Now the child shards are up. They are behaving just like any other replica following the primary, and we go on to replay the delta translog. So we took a last commit on the primary, and the commit may have been moved ahead, right? And we have to replay the translog from that point to tell the current commit. That concludes the phase 2 recovery. Now we wait in the final state of the recovery where we are waiting for child shards to be in sync with the primary. This means there are no more holes in the sequence number operations. And we have all the documents that are part of the global checkpoint. Like, we have basically all the documents that are part of the global checkpoint of the replication group on the child shards. Now there's an optional step here. Since we carried out a shard splitting query, we have a high number of deleted documents. Now, like, users may want to optimize their performance for after the split operation is carried out. So they can optionally execute force merges on the child shards to expunge the deletes, thus optimizing the performance. Once this is done, and by the way, this is the only expensive operation throughout the split workflow. The third step is to assign and wait for child replicas. The primary child primaries are ready, like whatever. So we basically created child shards, and they are behaving as replicas, but essentially they will be converted into primaries. And we do want replicas as a cluster, like as per the cluster index configuration, we want to assign the replicas on various nodes, right, to guarantee availability. So this is where we assign and wait for child replicas. Once the replicas are up, we acquire all the shard permits on the primary replication group. So we ensure that all the indexing requests on the primary and the child shards, right, they are blocked for a few milliseconds. So it's still online. We are not rejecting any requests. It's just that we are blocking the request by acquiring shard permits. And this is where we hand off all the traffic to the child shards. Now, whatever requests were waiting in the queue for the parent shard, they will be rejected back to the coordinating node and replayed on the child shards automatically. It's completely online. Customer will not see like any 4x6 or anything. And finally, we send a cluster state update to the master to mark the child shards as activated. So that completes our entire split workflow. I think Vikas, over to you.
So these are some practical use cases which depend on shard split today. So there is a use case where users require millions of isolated tenants to be created in the cluster. Of course, creating millions of indices or millions of shards under the same index is not a practical solution. So this probably, different contexts are set up within the shard where isolated segments have their own context and routes are routed according to the context. So the problem which this use case faced today is if millions of actors, if a subset of shards grow, I mean if subset of shards within the same index grow beyond certain extents, or if subset of shards become heavily skewed, then shard split can come into picture and help dynamically scale, split the shards and dynamically scale that index. So this is a good use case for shard split. Automated management can be set up where scaling policies can be configured or set up in the index lifecycle management policy plugin, where based on certain criteria, not just on storage, but also on various other criteria can be set up in the management policies, which can help users to automatically split the shards, dynamically scale the cluster without any manual intervention. We also talked about operational simplicity in the beginning, where it eliminates the need for oversharding or undersharding the index, and users are free to start with the fewer shards or fewer shards, and which can scale dynamically later as per their workload, as per the given set criteria in the lifecycle policies. And it also greatly simplifies the cluster design. Lastly, a future extension of this would be online shard merging, which can complete this whole story of dynamically scaling the cluster, where having this capability also embedded in the lifecycle management policies can allow customers to set up different criteria on the basis of which they can split or merge, and they can truly scale their OpenSearch cluster, keeping this elasticity in mind. So thanks, everyone. Please let us know if you have any questions.
Vikas, yeah.
So is physical split, is this exposed as an API, like the shard split API is today? Which is like, how is this being rolled? Like, is this custom that you have? Is it part of the next release?
Yeah. So this is in progress right now. This is not there yet in OpenSearch, but we are working on this and productionizing this. But we have a feasible working solution of this today.
Okay. So the goal is to release this as a feature. Would this replace the current shard split API?
No. So there is no shard split API today which exists. Index split API is there, but it is not going to replace that. It will be a new API for shard split, where users can configure it as an API, or we can extend this further as I talked about. It can be extended to be configured in the index management plugin itself, where we can, based on certain criteria, the shards can be split automatically.
There's another. Yeah.
Yeah, please go.
Is this intended to be compatible with document level replication as well as shard replication?
Yeah.
Yeah.
Let's say you have an index which is a 5-2 configuration, like 2 replicas. Goal would be to move to like a 6-2 or a 7-2, let's say.
have a replica for one of the shards on, let's say, node B, and that node B were to go down, how do you handle that resiliency to make sure that, I mean, how's that built in?
Right. So
Most of them you described as probably happening on the primary.
right on the primary node. Correct.
So how do you account for resiliency on one of the replicas?
Right. So this is a good question. So replicas basically, so there are different stages as Paras talked about. There are different stages of the recovery here. So we handoff is the last stage. So we don't perform the handoff as before. Once we have all the primaries and all the replicas of the shards, child shards, active on the cluster. So only after replicas of the child shard as well as primaries are active in sync with parent. What in sync means is that whatever child has, so even if parent goes down, child has all the operations required to be independently acting as the replacement of the parent shard. So with that, once that is done, once the primaries are in sync and the replicas are in sync, when the replicas are active, then we'll go ahead with the handoff phase, which is where the switch happens between the child shard and the parent shard. Okay, any other question? Thanks everybody for joining us today. And this is the RFCN design link, which you can go over to and ask questions if you have any other questions. We'll be here for any other questions as well. Thank you everyone.
Thanks a lot, everyone.